In virtual reality, handheld controllers are basically input devices, but can provide various haptic sensations to improve the immersive experience. But, typical handheld controllers have fixed shapes and sizes, so they cannot represent the various shapes of virtual objects. The user experiences visual and haptic data that are not consistent. To provide visual haptic congruent sensory experiences, researchers proposed shape-changing controllers as a solution. However, we do not have general computational models that explain the human perception of shape-changing handheld controllers. In this paper, we build a Visuo-haptic Crossmodal shape perception model for shape-changing handheld controllers, to provide congruent multisensory experiences to users in VR based on the concept of dynamic touch. Dynamic touch is the perceptual process of how you feel the weight, size, or shape of an object when you hold and wield it in your hand. Several researchers reported the significant effects of the moments of mass distribution on shape perception, based on dynamic touch. The static moment is related to an object's center of mass. The inertia tensor is a 3x3 matrix, and each element represents rotational inertia. The inertia tensor has 3 diagonal terms called the moments of inertia, and 6 off-diagonal terms called the products of inertia. The critical problem is that we cannot consider all physical variables of an object to build a perceptual model. Therefore, we conducted a computer simulation to identify the most important variables for haptic shape perception. The simulation results allowed us to choose the primary moment of inertia and the product of inertia as the important variables. They will be called MOI and POI. This figure shows an example of the range of several handheld controllers' MOIs and POIs. Also, cylindrical rods of different shapes have the following MOI and POI ranges. Then, we conducted 2 user experiments to confirm the perceptual importance of the 2 variables we selected. We investigated the human discrimination performance of the 1D length and 2D asymmetry of handheld objects. Participants wielded a physical object in their dominant hand and evaluated its perceived length or asymmetry. We obtained psychometric functions for the perception of length or asymmetry and retrieved the absolute or difference thresholds and the corresponding Weber fraction. Experiment 1 showed that the MOI of a physical object has a dominant effect on the perception of the object's length. The Weber fraction of length perception was very low, which means that people can discriminate 7% difference in MOI. In experiment 2, POI had prominent effects on the asymmetry perception of a physical object, with significant interaction with MOI. The sensitivity of POI gets worse as MOI increases. Therefore, MOI and POI are appropriate variables for object shape perception. We conducted the 3rd experiment to build a Visuo-haptic Crossmodal shape perception model. This model includes the properties of a handheld object as input variables, and the properties of a virtual object as output variables. This model suggests the best visual shape of a virtual object that matches the perceived attributes of a physical object, such as a shape-changing controller. The experiment was designed using crossmodal magnitude production. We obtained a regression model that explains haptic to visual shape perception. According to statistical tests, MOI and POI had a significant interaction on shape perception. This figure shows the regression model for shape perception. In actual applications, we can easily compute the physical configuration of a shape-changing controller that matches the visual shape of a virtual object using the model's inverse form, which uses MOI and POI as physical and perceptual invariants to bridge visual and haptic perception. Finally, we conducted a summative user study to assess the validity of our perception model. The experiment consisted of 2 phases. First, visual to haptic cross-modal matching, and second, user experiences. In phase 1, participants matched the shapes of virtual and physical objects. As our perception model predicted, participants could accurately identify a haptic object from a visual object. In phase 2, participants interacted with 5 virtual scenes. They evaluated user experiences under 3 haptic conditions. The best matching object predicted by our shape perception model, a mismatched object, and the original controller of the head-mounted display. Our visual to shape matching method improved the user experience between the virtual object and physical handheld objects. We hope our results in this paper could contribute to improving the hardware designs and rendering algorithms of shape-changing controllers for more immersive VR experiences.